Hello everyone, welcome to Unit 5. This week we're going to be talking about the use of covariate information in clinical trials. So up to this point we've learned that really we need to start with three things to have a clinical trial. And the first, we have a problem for patients. We have some proposed solution we're going to employ to help fix that problem, some kind of an intervention or treatment. And then we need an outcome, something we can measure and use to judge how well our treatment worked or didn't work. We also know by this point that if we can allocate thoughtfully selected group of patients randomly and an intervention group or a concurrent control, that's the situation that gives us the best chance to make causal and statistical inferences from the trial we have under the most palatable set of assumptions. Now, when we say we want to estimate something, what we're trying to estimate is the average treatment effect, which we've talked about a few different times over the course of the module. And estimates, regardless of what they're of, have certain desirable properties, and one of these is that the estimate is unbiased. And so in the frequentist sense, what do we mean when we say an estimate is unbiased? It means that if we can do this hypothetical long run of identical experiments, which we can't, right? It's a useful fiction. But if we could, and we were to calculate the treatment effect, the average treatment effect in every one of those hypothetical replicates, then the average of those average treatment effects would center on the truth, the true average treatment effect. And that's what we mean when we say unbiased. But as I've already said, we can't actually look at a hypothetical long run, infinite set of replicated experiments. This is a fiction that we use to help understand what inferences to draw from data. But at the end of the day, we're left with the trial in front of us, the actual study we did, the actual data we collected, and we have to do as much as we can with those data. Now, generally, I would say that we should never try to put too much stake or draw too much from the results of one single trial. And most people in evidence-based medicine and clinical trials would agree. Usually we want multiple trials before we can start to really feel confident about the effects of an intervention. But we still want to do the best job we can with the trial we have. And one way that we can improve upon our basic trial design is the use of covariate information. And we can use covariate information to, in some cases, greatly increase the power or the efficiency of our analysis in our trial. However, one of the trickier things when it comes to using covariate information is that it's an area of clinical trial design that people tend to get wrong quite frequently. There will be lots of published examples of the wrong way of doing things, and lots of clinical trial experts who have done things the wrong way. So it can sometimes be hard to overcome some of these incorrect ways of dealing with covariate information. And so here we're going to focus on, in this lecture, two particular ways in which people can frequently misuse covariate information. The first of these is about the proper way of selecting which variables to adjust for in an analysis. So once we've gotten done with the clinical trial and we're estimating this average treatment effect of our intervention with respect to the outcome, we can use, and we talked about this a little bit when we talked about ANCOVA and decomposition of variance, we can use other covariate information to reduce the sampling distribution of our estimator and then make it easier to detect even smaller effects or to detect make more precise estimates. And the way people go about selecting those covariates is often done incorrectly. So we're going to talk about that specifically. The other thing we're going to talk about at length is how to use what we're going to call the baseline. So we have covariates that are measured at baseline. In fact, we should almost never consider information that's collected after randomization, after baseline. But we have a very special covariate, which is if you have an outcome, let's say blood pressure. When I say outcome, I mean the thing that's measured at the end of the study in order to help us evaluate the effect of the intervention. But the variable you measured might have also been possible to be measured at baseline, and that's what we're going to call the baseline. And so there are different opinions about how you should incorporate proper baseline information with respect to the outcome. In particular, do you use a model-based judgment or do you use what we call change scores? So in this lecture, we'll go through both of these things. Okay, so to better understand the first problem, it helps to go to CONSORT. And CONSORT is our reporting guideline for clinical trials. It's developed by clinical trialists and experts. And this particular piece of language I've highlighted here is a very useful way to think about how we should treat covariates and how to not treat them. because the way they put this, balancing both known and unknown prognostic factors, is incorrect. And the point here is that randomization doesn't have anything to do with balancing known and unknown prognostic factors. It will do that, but that is not the purpose. The goal is to create exchangeable groups with respect to the outcome. The thing that we're interested in is the outcome, not the covariates themselves. And if you think back to when we talked about the causal inference lecture, we know that we can't see any counterfactual for any particular person, but if we take a group of people, a large group of people, we randomly allocate them to two different groups, we know that the distribution of those outcomes will be roughly the same, especially if we've properly powered and designed our study. I just want to be clear that the outcome is the thing that we're going to measure into the future. So we will never be able to observe the outcome under the control condition for both groups, because one group's going to be in control and one group is going to get the new intervention. So we are assuming that the groups will be exchangeable with respect to the outcome, a thing that we measure in the future. And as long as we get exchangeable groups, then we're happy. Now, that said, we can use covariate information to say something about how exchangeable those groups might be, because we know if we have an outcome measured in the future, well, that outcome will be able to be predicted by some set of predictors. Things have other causes and influence that don't have anything to do with our trial necessarily, but things that we can collect. So if we can measure those strong predictors at baseline before we randomize people, and this is very important, then later on we can adjust for them in our statistical models. Unfortunately, that's not really the way that people go around doing this, and they tend to take a quite backwards and counterproductive approach that we'll describe now. So what people often do is they report what we call a table 1, like this one in a clinical trial. And what you'll notice here is that here we have it's a 3-arm trial. In this particular example, it's part of the discussion reading this week. And we had 3 groups assigned to a placebo and 2 different interventions. And here we have a test p-value. And so this is a very common thing to see, and it's just some bog standard statistical test to let me know if the distribution of whatever this thing is here, age in this example, sex, smoking, and so on, if those distributions are similar enough across the 3 groups, or if we detect a significant, quote-unquote, significant difference among them. And what people often do is they produce a table like this one. They go and they look at the variables where they found a significant difference, a difference between the groups with a small p-value, and then they decide to adjust in their statistical models for those variables, that variable or those variables, whichever ones they find. So the problem with this is if we go back to our causal inference lecture, we talked about simple confounding, right? Where we see an association between X and Y, and we're trying to explain why it's there. It could be explained by a causal relationship, or it could be the presence of a shared parent, right? So we had the example of, we had my graying hair color, we had my risk of heart disease, and age. So if I see an association between gray hair in people and risk of heart disease, if I were to adjust for age, then in all likelihood, that association would go away, and giving people hair dye wouldn't do anything about their heart disease. And the important thing here is that the confounder had to be a parent of both the exposure and the outcome. Now, when we talked about clinical trials and why randomization is our most kind of palatable set of assumptions for making causal inferences, it's because we know that if we randomize allocation, there can be no arrows pointing to X, and so there can be no confounding. And that's shown and proven by the DAG. As long as I have no arrows pointing to X, there's no causes of X, and there can't be a cause of X if X is a randomized allocation because it's completely at random, then I can't have a confounder. Thus, I can't have a confounder explaining my association between these things. So this is essentially the DAG that we're talking about. If we start to think about, I'm going to pick variables in my table 1 that are associated with exposure, or the random allocation in this case, and I'm going to adjust for those things. Well, this is a completely pointless adjustment unless there's a relationship between that predictor and Y. And so that leads us to what Consort goes on to later say, and this they get quite right, is they point out that this idea that these significant tests are unfortunately common. And so for some of you who've read a lot of trial papers, you'll have seen those tables with the p-values over and over again. The paper that we looked at this week for the discussion has them, and I'm one of the authors on that paper, and I'm saying I don't particularly like them or they don't make sense to me. They're a very common thing to do. And there's a reason beyond what we're talking about. They're not useful for selecting covariates to adjust for, and we'll come to a demonstration of this in just a second. The other thing is that the results of the test are a foregone conclusion. If we think about what a statistical test is, say it's between two groups, we have a type 1 error probability that we usually set around 5%. It's the probability of rejecting the null of no difference when we shouldn't. And we know if we're randomizing people into two groups and we happen to see a significant effect, we already know that that's a false positive. And so that's why they say that this kind of hypothesis testing is superfluous and it can mislead people. And so the misleading part is what we'll talk about next. So in general, this idea of screening through table 1, finding the significant predictors and putting those into a model is a bad idea, but it helps to also demonstrate why this is the case. So what we're going to do here is we're going to use some simulations in this lecture. And simulations are something that I find very, very useful. We can even think about statistics sometimes as trying to understand what a data generating mechanism is. In other words, we make statements about how we think the universe works and how the universe generated the data we see. We build models to mimic our thoughts and then see how well the data match up with the model. And so in simulations now that we have, fast computers on our wrists and everything else, what we can do is we can simulate a very large population of patients, right, of values. And in this instance, we've done that, and then we've got one normally distributed outcome. So this is the thing that we imagine we would see at the end of the trial. It can't be measured today, it can't be measured at baseline. It represents the future, something we can't observe. And in the simulation, we've added 20 different covariates. So 10 of them are predictors of the outcome. And that means when I set up the simulation, I made it so that the outcome was a function of those 10 predictors, so that there will be a correlation between them. And then 10 of the covariates I've included in the simulation have no relationship to the outcome whatsoever. So what we want to do is demonstrate what's the best way to use this information. And so this would be a distribution of our outcome. It's just standard normally distributed with a mean of 0, a standard deviation of 1, and that's our bell curve. And so this is a large sample. You can see there the count, goes into the tens of thousands. It's a large, hypothetical simulated sample of patients, and this is the distribution of the outcome. And then we can look at the relationships between the different covariates and not. So you'll see the ones that are labeled as non-predictors. Those have a horizontal line here. So there's no relationship in the simulated data, and you can see all the data points, 100,000 data points here. There's no relationship, just a blob with a horizontal line. So the non-predictors, there's no correlation or association between those and the outcome. If we look at the predictors, they're set up to have different strengths of association. And so you can see that there, for those, you can see a tilt. So there is some kind of a correlation or association there. And for some of these particular G, I, and J, those the degree of association is even stronger. So those are quite strong predictors of our outcome. So we've got non-predictors and we've got predictors. So the next thing we need to do is we need to go through and think about what these table 1 tests tell us. And so what we'll do is we'll take from this population a sample of 100, right? So I'll just randomly pick 100 out of the 100,000 simulated patients. And then I'll randomly assign people to one or two study arms, active and control. And then for each of the variables, the 20 covariates, we'll do a simple test of whether we see a difference between the arms for the things. And if I do that and I plot it, what do I see? So out here, these are p-values. So some things have very large p-values, some things have very small p-values. And in this particular sample from our large set of simulated data, we see a significant difference for non-predictor C. So we do see, and this is out of 20, and we just happen to have seen one, which that fits in really well. If we expect the number of false positives to be 5%, then 1 out of 20 is 5%. But of course, we're not always going to see that. Will be some variation depending on our specific sample. So if we were to actually repeat this over and over again, so we have our simulated data, and now we're going to sample 100 patients over and over and over and over again and do that a whole bunch of times, and then look at the distributions of how these things fall out. Right, so we take a new sample, assign it to study arms, test all the covariates again, and keep track of all the significant differences. And so what do we see here? So if I look at the proportion of times that I find a significant difference in the outcome, we're pretending like we can see the future here. We've simulated the data, so we know the truth. I know if there's a baseline difference between the outcome as reflected by a statistical significance test, and that comes out to just about 0.05, which is exactly what we would expect. We'd expect to see that 5% of the time. So had I simulated an infinite number of replications, that would be bang on 0.05, right? So it's very, very close, and that's just a little bit of sampling error. How many should we expect for the non-predictors and the predictors? And the answer is we should expect there to be one or more significant results out of a group of 10 predictors 40% of the time, or a portion of 0.4. And that's because each of them individually has a 5% chance of being a false positive. And we take the 1 minus that up to 10th power, and that's going to give us 40%. All right, so again, whether it's a non-predictor or a predictor, whether it's something that's not related to the outcome or is, you get the same answer. All right, and sometimes you get 1, sometimes you get 2. So this is 1, 2. You even get 3 and 4, so you can get lots of significant predictors and non-predictors. Something that's worth noting here is that we know the predictors are strongly related to the outcome, but that doesn't have any influence on how many differences we see. It has nothing, in other words, it has nothing to do with the outcome whatsoever. It's all about the sample arm. So this is the big clue why this isn't, this is how we should do this. Now, we can make it a little bit more interesting than this. We could predicted this and it fits in with what we could have predicted and moving on. What if I have a significant difference in a non-predictor and I want to look at how often I will also have a significant difference in the outcome? Now remember, the outcome is something we can't see. So we're using a significant, if we do this the wrong way, we're using a significant difference in a non-predictor to make some inferences about a difference in the outcome. In other words, a violation of our assumption of exchangeability about the outcome that we'll see in the future. And so given that I have a significant difference in a non-predictor, how often do we think we'll see a significant difference in the outcome? And you just take a minute and think about that and pause the video and see if you can make a guess, and then we'll go on. And so the answer here is that essentially there's no relationship whatsoever. So if I have 0 significant non-predictors, the 10 variables that don't have any relationship to the outcome, I see almost 5% of significant differences for the outcome itself. So the proportion of simulations where we have a significant difference in the outcome is right around 0.05, 5%. If I have 1, it's around 5%. If I have 2, it's around 5%. And 3 and 4, I just have so few examples of that we don't happen to see any. But the take-home message here is that the number of significant non-predictors has no relationship whatsoever to a quote-unquote baseline imbalance in the outcome. In other words, if I'm worried, I've done a clinical trial, and I know that a clinical trial, if randomization has been done, is unbiased, which means if I were to run this hypothetical infinite number of trials, my answer for my estimate of the average treatment effect would eventually center on the true average treatment effect. I only have the one trial in front of me. I'm worried that my 2 groups might not be exchangeable, which will interfere with how I interpret the results of the trial. Well, looking at the number of significant non-predictors, things that I know don't drive the outcome or not predictors of the outcome, it tells me nothing. It tells me nothing about exchangeability whatsoever. This will become super clear when we look at the next one, which is if I have a significant difference in a predictor, then how often will I also have a significant test difference in the outcome? So think about this one for a minute. And so here's the answer there. You see this very clear relationship. So if I don't have any significant predictors, and this is a very crude way of thinking about it, but it shows exactly what we want to show. If I have none, then my probability of getting a significant outcome is less than 5%, and it goes up. It goes up with each time I add a significant predictor. So here in 4, these are simulations out of a whole bunch of simulations where there happened to be 4 significant difference among the variables that are key predictors. And when that happens, it's not surprising that we're more and more likely to find a significant difference in the outcome. However, it's also worth noting that even when I've got 4 significant predictors, that it's still more likely to have a no significant difference in the outcome itself. And so why is that? And this really gets to the heart of why randomization doesn't do anything, to balance the covariates per se. It's really about the outcome, because an imbalance in one covariate could be offset by imbalances in other ones. In other words, if we take each individual person, they're going to be some combination of different levels of all the predictors. And where you're high on one predictor, you might be low on another. And so a lot of this stuff just cancels out. So even though we get a case here, we get a table 1 where 4 different variables among things that we know because it's simulated, things that we know are predictors of the outcome. Even then, you're only going to see a significant difference in the outcome itself about half the time. Now, let's think about how to use this information. So hopefully at this point we understand why it doesn't make any sense to go through table 1 and just pick out the significant things and use those. But what can we do? And so we can look at this, actually model some stuff. So what we're going to do is we're going to take our simulation, we're going to add a constant treatment effect to the active arm. And so this is simulating the idea that this randomly allocated arm actually comes with something that does something. We're going to add something to their outcome. And we're going to estimate the average treatment effect. And importantly, we're going to pay very close attention to the variance of the estimator. And I'll show you where that is on the regression tables. And we're going to adjust for predictors or non-predictors, and we'll see what happens. So this is the outcome in the simulated data. Right? And so what we see here is the simulated data and then taking a sample of 100 patients. And so this is the active arm and the control arm, the distributions. Right, so the area under these curves is equal to 100%. So this gives us a relative idea of the frequency, the relative frequency of different values in our data set. And while the curves aren't completely superimposed, you can generally see they're both roughly centered here. There's a little bit of a bimodal thing going on here, but that's just sampling variation because it's only 100 patients or 50 in each group. But you can see that there's very little difference between the mean, which you can imply to be the mean of these two distributions. And so what we've done now is we've added a little bit of a treatment effect. Now it's a subtle one. It's the size of a fraction of a standard deviation. But this is the difference here. It just shifts that active control arm just over to the right a little bit. And that's the distinction. That's what we're trying to detect in these two groups. So the first thing we should do, we can run a couple of regressions. And in this instance, this is just to kind of get ourselves grounded in what we're going to look at later. And so what I have here is I have 2 different regression models, 1 in each column. And here the first one, I have an outcome, and that's just from the sample before I've added a treatment effect. And if I look at it, this is the effect of the active arm. And what it says is that the active arm, the value of the outcome is 0.21 higher than it is for the control arm. Now that's got a wide confidence interval and a large p-value. Right? But even if I just looked at the crude association between the two arms, I'd see a small difference. If I look instead at this column, which is the other model, now what I have is I've added my treatment effect, my true treatment effect, this is what the drug does or whatever it is we're testing, of 0.2. And so that takes this what we'll call a random difference between the two groups, and it adds in the structural difference being the effect of the intervention. And so if we were to run this analysis, we would come out at the end of the study and we would conclude that the treatment effect, our best estimate for it was 0.41. We know because we've simulated the data it's actually 0.2. And here we conclude it was a small p-value, and you could go from there. Although a p-value of 0.05 should never be anything anybody gets too excited about. All right, so that's just kind of showing what our simulation has done. So this is our kind of the random difference we got just because of sampling variation between the active and control arm. This is when we take that sampling variation, we add variation caused by a constant treatment effect of 0.2. All right, so moving on. What happens when I start to add covariates? So the first thing to look at, this is just where we started before. This is what happens when I add that significant non-predictor. When I add the significant non-predictor, what happens? Well, first of all, this doesn't affect my estimate of the treatment effect whatsoever. My p-value goes up ever so slightly, and the reason is because I'm adding essentially noise to the model. So I'm making my estimator more variable. I'm using up information in a wasteful way. So adding a non-predictor to a regression model doesn't help us at all. In fact, it hurts us. And we can see that the estimated relationship between the non-predictor C and the outcome is practically zero, right? Minus 0.01. So that confirms there's no relationship, zero relationship between this thing and the outcome, and it hasn't affected our estimate of the treatment arm and the outcome, but it has made things a little bit noisier, just a touch, and that's popped the p-value up. All right. So now what we'll do is we'll come over here, and instead of adding that non-predictor, we're going to add predictor G, which I told you is one of the strong ones. So what happens here? So now I get a coefficient of minus 0.53. That means that every unit increase in predictor G comes along with a 0.53 unit decrease in the outcome. And that's a very small p-value and a very strong association. So these two things are inversely correlated, and that's accounted for in the model. Now, if you have a look up here, you can see that this has led to somewhat of an attenuation of the effect of 0.41 I was seeing before. And the reason for this is that this imbalance, this random sampling variability imbalance here at 0.21, is partly described by the imbalance due to predictor G. And so when I adjust for this predictor, then it kind of resolves some of this imbalance, and that gets taken out of our estimate of the treatment effect. Now again, we know all this because we've simulated it. When we're doing this with real data, we're kind of, we're shooting into the dark trying to make guesses about what all this stuff means, but these are the principles behind it. And the other thing we can consider here is that we have the R squared, and so this is the percentage of the variance that gets explained by the model, and here it's very little, 0.01, 0.04, 0.04, so 1%, 4%, 4%, but now by just adding that one strong predictor, I'm explaining 34% of the variance in the outcome. So I've added a very strong predictor here indeed. Finally, if I take a model where I just take the 3 strong predictors we had, leaving out the other 7 that I know are predictors as well, G, I, and J, and you can go back and look at that plot, we had the minus 5.8, and these two are just as strongly correlated, but in the positive direction. And now look what happens. Now I've got what I know, because we've simulated these data, something that's very close to my true treatment effect of 0.2. It's no longer the imbalance of 0.21 plus the treatment effect of 0.2 equaling 0.41. It's just the treatment effect. Because if I look down here, I've now explained 81% of the variance in the outcome. I've removed that, is what that does. And when you remember when we talked about power early on in Neyman-Pearson hypothesis testing, when I remove variability in the overall variable, I lower the variance of my estimator. If I lower the variance of my estimator, it makes it easier to see smaller effects. And if I look here, this is the standard error of my estimator. We started, it was equal to 0.21. The specific numbers, they don't matter themselves, just the relative differences. It's 0.21 across the board. When I've added one strong predictor, it goes down to 0.17. And then when I've added 2 more strong predictors, is equal to 0.09. And so if I assume that this treatment effect is a normally distributed thing, this is the standard error of that distribution, and that results in a p-value of 0.03, so even smaller. So by adjusting for strong predictors, we've made a better estimate, we've removed some of the effect of the quote-unquote imbalance, we've got a more precise estimate with a smaller standard error for the estimate. So in summary, when we do this, what are we going to do? Usually adjusting for predictors, the outcome is a good idea. And you get a fair number of investigators who, out of fear or concern for adjusting for things, putting things in and out of models, seeing p-values move around, would prefer that we don't adjust for anything at all. We just accept that the randomized allocation gives us an unbiased estimate of the treatment, and unbiased is unbiased, and that's a good thing. And so they would just prefer that we do that and don't do anything else. And that's not an unreasonable approach to take. That's a very conservative approach to take. The problem with it is that if we can improve the efficiency of the study, meaning we can detect effects with more precision with the same sample size, or we can define even smaller effects at the same sample size, it means ultimately that we can recruit fewer patients. And recruiting fewer patients and exposing them to unknown risks is probably a good idea. or we can get more information out of our study the way it's designed. So not using covariate information, there's an argument to be made that that can be quite problematic. However, when we do that, we can't select covariates just based on these Table 1 tests. Not only does it not work, we can see that it's actually counterproductive. If we wrongly adjust for something that was significantly different at baseline, but that does not predict the outcome, we're just adding noise to the model. So now we're making, each patient we have enrolled in trial, the information we get from those patients is degraded just by that little bit, and that's not a good strategy at all. So instead, what we need to do is we need to identify strong predictors. Now, I knew which predictors were strong because we simulated these data. And so this is the real challenge for you as the clinical trialist and the investigator, is that these strong predictors have to be identified prior to the study, before you recruit a single patient. So they need to be in the protocol, they need to be in the statistical analysis plan, and they need to be pre-declared. And the reason they need to be pre-declared, we hinted at when we talked about outcome switching, and how registration has kind of changed the reporting of clinical trials, where all of a sudden we see a lot more null effects in the literature now. Outcome switching is one way that we can make sometimes reasonable sounding decisions about how to analyze data, and then see p-values move around, and then we're naturally inclined to select choices based on what it does to the p-value. We can do the same thing by adding and putting in and taking out predictors into a statistical model. We could add stuff and take stuff out until we get the result we want, which is usually people wanting a p of less than 0.05. And we want to avoid that. And so what we want to do, if we're trying to avoid that kind of questionable research practice, is we want to nominate our strong predictors before the study begins and make sure those are registered and out in the open. And then when we do our final analysis, we only adjust for those things. And we don't not adjust for them. We said we would adjust for them, so we adjust for them. This will help us prevent any kind of, not just ourselves from ourselves, but it also helps improve the integrity of the trial to outside observers. And then you get everyone's utmost good faith. That means it falls back to you as the investigator to understand your outcome. You have to understand the outcomes you're using because you need to understand what things tend to predict them. And so if you're someone who's an expert in an area of science and you've read all the literature, then you can probably sit down and think about your intervention and how you're going to measure the outcome. And you can probably come up with 4 or 5 or 2 or 3 or whatever of the strongest predictors. And those are the things. You're not going to get them all, nor should you try to. But things that you can measure at baseline before randomization, things you know are going to be strongly predictive of the outcome. If you can measure those things, get them into your protocol, and then adjust for them, that is the best strategy for how to deal with covariate information and improve your study. All right, so we'll go on to the second main point for this week, and that is this issue of adjustment for baseline versus change scores. And this is closely related to what we just talked about and doesn't require, I don't think, nearly as much explanation, but we'll go through an example. And again, it's the same idea. Sometimes trialists are very worried that the distribution of the baseline is different between the study arms. And that way, it's just another covariate. The baseline is something, if we think about our outcome as something we measure in the future, then our baseline is our measurement of that same variable that we can do today prior to randomization. So the outcome of my study might be blood pressure measured 3 months post-hospitalization, but I can get your blood pressure today, and that's my baseline. We call that the baseline, but it's just another covariate. And so if we have people who happen to get into the active arm, whose blood pressure is higher than we would expect based on the regular distribution of it, just by chance, then that's going to get tied up with our treatment effect, the outcome, blood pressure measured at the end of the study, if those two things are related. And they will be, because they're measures of the same thing at 2 different time points. And so people often think that the solution to this is to create a change score. So in other words, you take blood pressure at the end of the study and you subtract blood pressure at baseline from that, and that gives you the difference in blood pressure over the course of the study. And that supposedly deals with this issue of any kind of baseline imbalance in blood pressure at the beginning of the study. And that's not the right way to do it, because again, it has to do with the variability of the estimator. And so we'll demonstrate that. And so the real thing you should do, the correct thing to do, and this is completely non-controversial among statisticians working in clinical trials, is that you just adjust for the baseline variable like you would for any other strong predictor. And that should tell us too that when we can find a baseline, when we have an outcome that I can measure prior to randomization, that's well correlated, that's strongly correlated with the outcome at the end of the study, then that's a strong predictor. And in fact, some people, would suggest, or it makes sense to keep that in mind when you're thinking about your outcomes. If you're thinking about outcomes for your trial, things, especially in surrogates as well, is things that you can measure at baseline means that you can improve the power of your study by adjusting for those things at baseline. And so that it's a good decision to use that kind of a variable, something that gives us a baseline measure. All right, so another simulation for this. So we're going to say we have the same outcome measured at the end of the trial. We can't see the future, but we can here now because it's a simulated data set. And I also have a measurement of the same variable made prior to randomization called the baseline. And we'll just compare models here that use either change scores or adjustment for baseline, just like we did in the other models, and see what happens. All right, so this is our correlation between baseline and outcome and the data we generated. All right, so the correlation is very weak, so 0.19. All right, so if I measure this at baseline, it tells me something roughly about where I would expect you to be at the end of the study, but there's lots of noise, right? So if I take this person here, these are all people along this line that had a baseline value of 0, but plenty of them have very high values at the outcome. Plenty of them have very low values at the outcome at the end of the study, right? So it's not a perfect, the correlation is 0.19. Now, I can look at a number of different models. So this is just, again, to center ourselves. This is the outcome. Now, I've sampled a new group of 100 patients. I've looked at the difference in the outcome in the active arm, and this is before the effect of a treatment. So here it's 0.06. So there's a tiny little difference in the distribution between the active arm and the control arm that's there in the data before I've done anything. Here I've added the treatment effect of 0.2 units, and so that goes from 0.06 to 0.26, okay? I've moved that away from the null value a little bit, so the standard error of the estimator is the same, 0.21, 0.21, but the p-value gets a little bit smaller because I've moved it away from 0. Now here, what I've done is I've swapped out the outcome measured at the end of the study with the change, right? So I've calculated the change between baseline and at the end of the study, and I've put that in instead. So what this says is that in the active arm, the change is 0.5 units. So people in the active arm, they tended to increase by 0.5 units on average. And actually you see here that the p-value is quite small, but again, it's because I've changed the scale, moving this away from 0. And the p-value here just tests the null hypothesis of 0 for that particular dependent variable. But here you can see the standard error of that estimator is 0.26. It's wider, it's noisier, right? And that's important. So then what happens, if I go back, and now I'll do this again where I have the proper outcome measured at the end of the study or the change in these two, comparing these two models. But what I'm going to do is I'm going to adjust for the baseline, right? So when I adjust for baseline, this is kind of interesting. What happens? So now I've adjusted for baseline. I see my effect, my estimated treatment effect here would be 0.31. I see that there's a small enough p-value, and then I get an effect for the baseline on the outcome, and that's equal to 0.22. Here, when I do this, I adjust for baseline when it's the change score. Lo and behold, I get the exact same effect. Now, what is going on here? If I do the outcome, like just the measurement at the end of the study, or if I do the change, if I adjust for the baseline value, I get the same value for the coefficient. So the way to think about that is, when we adjust for things in a statistical model, we think about that as holding it constant. We're like using a statistical model to control for that variable. So if I take two people with the exact same baseline value, in other words, I hold their values constant, and I look at their outcome, well, the outcome holding baseline constant is going to be the same thing as the change, right? If I have a situation where two people start at the same point, well, their change over the time period is going to be completely described by where they wind up and vice versa. So adjusting for baseline makes these two things the exact same thing. So in other words, it makes no difference whether I use the outcome at the end of the study or the change score, given that I'm going to adjust for baseline. I get the same answer either way. And then I can pop in my other strong predictors And lo and behold, I've recovered what we know to be very close to the true treatment effect of 0.22 again. So again, the moral of the story here is that the change score doesn't solve any problems for us. And another way to look at that is if we look at the relationship between the baseline value and the outcome, it's positively correlated, right? So every unit increase in the baseline variable is associated with a 0.22 increase in the outcome variable. And so that's the concern we have. That's why we're adjusting for baseline, because there's this correlation between the two things. And we're worried that baseline imbalances in the baseline measure are going to be tied up with our estimate of the treatment effect. And so we make the change score to deal with that issue. But if you'll notice here, the change score is also correlated with the baseline. Right? People who start off low are more likely to have a greater change because of regression to the mean, our old friend. Right, so now we see every 1 unit increase in the baseline is equal to a decrease in the change. And that's a highly significant effect. So this idea that we're going to use change scores in order to remove the correlation between the baseline and the outcome, the same variable measured at the 2 time points before randomization and the end of the study, well, actually, we're just using an outcome that's just as correlated as it is for the outcome when we use the change. So this doesn't gain us anything. The only solution, again, is making this adjustment. And once we've done that, then it doesn't matter which outcome we use. Here, we didn't adjust for it 0.26.5. This is a 1 unit increase, this is a 0.26 increase in the mean outcome comparing active to control. This is a 0.5 unit increase in the change over the study comparing the active to the control. But once I adjust for baseline, those become the exact same thing. And then this is just the plot from Stephen Sin's reading, and the point he makes here is if we have an outcome and a baseline, and those things are correlated to a certain degree, and ours was around here, around 0.2, and we're looking at the variability of our estimators, right? How noisy our estimators are. If we look at the outcomes, the change score here, it's the highest. When we use the change score, the variability for that thing is much higher than it is for either just using the outcomes themselves, or this analysis covariance just means to adjust for it in a statistical model, which we'll talk a lot more about 2 more units. And so you can see that when these things are small and not very correlated at all, you get a really big drop off. Eventually the change score becomes more efficient than the use of just the outcome itself, but it's never below the variance of the estimator when we just adjust for it in the model. So in other words, this is always the right solution, or the right choice, is to just adjust for it. There's never a situation where you're better off doing the change score. So the summary there is just to adjust for baseline like any other covariate. And before we wrap up, I'll just add this one aside. This is advice that only applies to randomized controlled trials, because we don't get big skews in the baseline if the thing is properly designed, but it can be very wrong for observational studies, but we don't have to deal with that. Okay, so thank you for listening. Bye.